Okay, so we're going to start. So I stay close to them because so they can see me on Zoom. So thank you very much for joining the seminar of GIST. And so today we have the great pleasure and honor to have Ian McLaughlin from the Singapore Institute of Technology. So Ian has been working on a lot of different things, right? But his core expertise, I would say, or maybe it's my filter because it's a common interest, essentially speech processing. Everything revolves a little bit around speech and audio. And, you know, one note to say also that Singapore Institute of Technology, especially for those who joined more recently, is a very long-term partner of the University of Glasgow, in particular of the School of Computing Science, because we have a joint program that we deliver together, and we have colleagues actually of the university that live and teach in Glasgow in collaboration with the colleagues of the Singapore Institute of Technology. So I think it's very nice to have you here today, not only for the talk, but also because, I mean, we are trying to establish a little bit more a partnership that goes beyond teaching and involves research too. So thank you very much.
Yeah, thank you, Alessandro. I think it's really very good to be here. And can you hear me online? Any reactions? Yes, no? Yeah. Okay, thank you. Yeah. So thank you for the people who've turned up in person. It's always good to see three-dimensional human bodies. And thank you for the people who turned up online. And I'm going to try to talk to you a little bit about something that I think is absolutely fascinating, and I hope you think is slightly fascinating, okay, which is speech and audio AI. And it's an area that I've been working on for many, many years. And I've seen a lot, 30 years, I've seen a lot of things, a lot of shifts there. So I'll try and give a little bit of my perspective, and maybe from that, talk about opportunities and direction of travel of what we can expect in the future. And you'll be the people making that future. So this is kind of an interesting thing to do. I'll introduce myself a little bit because it's kind of weird, the stuff that I do. I have like a talk with 15 slides about what I've done in the past. So I kind of pared it down here to one slide. And that just has to have a globe, and it shows how I started in the UK and I went to Singapore. And then a few years I got sick of Singapore. I went to New Zealand. I got a New Zealand passport, and my kids were brought up in New Zealand. And after another 6 years, I got a bit bored of New Zealand. I went back to Singapore again for another 6 years. Then I thought I should go and work in China. China's great, right? So I got a job in China, and I worked in China for 3 years. And I came back to the UK. Then I went back to Singapore again at the first possible opportunity. There's a theme here. Can you see what the theme is? Yes, I can't keep away from Singapore. So let's hope that some of you can catch a bit of that theme at some point. And you can also say I've worked in universities and I've worked in industry, but most of my last 20 years has been in university. And it's kind of like, couldn't make up my mind how applied my research should be. Should it be like totally theoretical? It should be partly applied. And then I kind of switched between, and now I know I'm good in academia. But Singapore Institute of Technology is a bit different to other universities. So forgive me if I give you 2 pages of propaganda about Singapore Institute of Technology. After all, they are paying my bills. So here we go. It's a startup university. It doesn't mean that it's just starting up now. It means that the mentality is startup. Things are new. When I started a research project there, typically the kind of project I'm doing is something they've never done before, which can give me big headaches, but also great opportunities. It was set up as a teaching institution and recently became a research and teaching institution. And the teaching that Singapore Institute of Technology has been doing, at least for my part of it, has very much been helped and initiated by the University of Glasgow. You helped to set up a degree program that is actually a best degree program in my view. We have 5 clusters in the university. Other universities might call them faculties or schools. And the ICT cluster is the biggest one by student count. That's the part that I manage. And we are essentially computer science and computer engineering, maybe with a bit of informatics thrown in. That's what we cover. We call it ICT because that's the industry sector that the Singapore government views as an economic generator for the country, ICT as a whole. I kind of think it would be nice to be called computer science, but then again, we wouldn't get so many industry grants. So we'll stick with ICT. We have right now 3 full professors, about 20 associate and 20 assistant professors. We're a bit top heavy. I've been recruiting heavily. A lot of people have joined in the last year or two. We just started a doctorate program, PhD students, in 2022. After many years of not being allowed to take PhD students, and this is becoming quite successful. So you can see we're starting up. We're doing things here that, well, University of Glasgow has been doing for 400 years, and we're just starting that now. And it's quite exciting to be part of that. Many of you will know Jeannie on the slide. I shouldn't point on the screen here because people online can't see it. So on the slide, it's the picture at the bottom, and there's 2 kind of light green boxes. And it's the right-hand box there, that's Jeannie. Okay, I'll point, I'll give you. And she's been here, she's visited you, and she's my right-hand person. She's in charge of the 4,000 students that I have in my cluster. Just to put this into context, Singapore's got 5 universities. We're the 3rd biggest. Just the bit that Jeannie manages is bigger than, let's say, Singapore University of Technology and Design. I mean, the bit that Jeannie manages is bigger than the entire next university in Singapore. So it's quite significant in terms of income and also economic future for the country. And we've got 13 undergraduate degrees. As I said, our flagship degree is probably computing science, which is run half and half with SIT staff and University of Glasgow staff. Mostly University of Glasgow, Singapore. That means your colleagues who are working permanently in Singapore. We, inside the Singapore Institute of Technology, we work with many people. We work with many industries, 200 at the last count. And we are arranged at the moment into 5 research groups. 2 of these have been inspired by the University of Glasgow. I'll just quickly tell you what they are: cybersecurity, AI, human-computer interaction, emerging areas. That's the name of the group for things that I can't think where it should go. I just put them in there. If you don't know what it is, it's emerging areas. And for that one, we have this thing called the 5G Translab. And 5G Translab is like this. Singapore government said, hey, we've invested billions in 5G infrastructure. No industry is using it. You universities, get some projects together. Teach students how to use 5G and put them into industry. And we said, well, we need some money for that. So they gave us $20 million. And we just do all these projects to do 5G plus speech, 5G plus cybersecurity, 5G plus autonomous vehicles. Anything you can do with 5G, we found out. It's great. You get research funding, you get to travel, you get to publish papers. It's good. And S3 is SIT systems section. And I've got some of the names. Many of you who've had a link with SIT would know who Malcolm is, one of my colleagues. And he used to be in charge of liaising with the University of Glasgow. Okay, that's the propaganda bit over. Let's talk about the fun stuff now. I'm going to talk about speech and audio AI. I've got 4 different parts to this talk. The first part is speech technology. The second part is speech communications. The third part is auditory analysis. And the 4th part is a robot, which is my representation of the future. Okay. Why? Okay. Well, let's just look at all of the different topics that this can encompass. So I've divided them into 3 parts. Part 1, part 2, part 3 on the left-hand side of my slide here. The types of technology that we're dealing with, most people will think of speech recognition. They'll think of when you pick up your phone, you say, hey, Google, or hey, Siri. I won't say it loud because everyone's phones will light up. Sorry if yours was lit up. And that's what people think of when they imagine speech technology, but there's so much more to it. There's speaker recognition, there's language identification. If you're in a multilingual country and you call up a call center, how quickly can the call center route your call to the correct listener? There's things like topic detection. This is used when you're annotating videos, for example. It's used for looking at news reports. many other uses for topic detection, but quite a lot of it's information retrieval based. Emotion recognition in that call center. If somebody's calling up and they're extremely angry, then you would route the call to the person who's very good with dealing with angry people. If somebody calls up and they're really happy, well, anyone can deal with that. Right? Or maybe if you're in a call center and if somebody calls up and they're extremely upset, you would think that maybe they'll put them in a shorter queue. Actually, they don't. They put them in the longest queue. At least that's what I find. Okay. But we can imagine this technology has great uses. Diarization is the task of automatically annotating meeting speech. So who spoke what, when? It's a very challenging task. Speech communication is where this all began. It began with a humble telephone, the ability to speak over long distances. And it's kind of evolved into our mobile phones today, which of course are more often glued to our eyes than our ears. Auditory analysis actually is as big as the entire topics above that I've talked about in speech. There's so many things you can do with auditory analysis, and I'll talk a little bit about that, some of the fun things in a while. And then the stuff I don't have time for, but I actually love: music, entertainment, synthesis, non-human audio, animal calls, different kinds of sounds. There's lots of things there that you can use sound for. It is as pervasive as video, but it doesn't get as much research attention normally. Why I like speech is it's because it's our primary communications mechanism. Okay, it's the way that we most often communicate things to people. Okay, you can say facial expression is one way, but you don't always look at someone when you're talking. You may be away, or you may be talking to a group of people. It's how we convey ideas. It's how you convince somebody to vote for your political party. It's usually through a speech, or these days maybe through social media. If you go to a lecture, you can look at the slides, but I can tell you, without listening to the lecturer's voice, you don't get much information. Maybe even if you do, you won't get much information, but I can tell you, without speech, it's a lot worse. You go to a court of law, arguments are done by speech. If you go and worship in a church or a mosque, you're listening to speech. It's conveying ideas and information. It's important. It's responsible for regulating information flow and relationships between people at all levels. But don't do that to, can you help me, please? It also is one of the best indicators that we have of what's inside our brain, because often what's inside your brain comes out in actions, but it can come out in your speech first. So analysis of speech can tell you something about what people are thinking. Until we get real active brain-computer interfacing and thought police, the speech is a good mediator. There's lots of things in there. And if we had an AI that was perfect, and we had some ability to pick up as much information from speech as we can, which, let's face it, is where we're going with this technology, it's the end point, then we can find out from a piece of speech who is speaking, what they're talking about, what they really mean, and the relationships. By listening to how someone speaks to someone else, you can tell, are they in a supervisor, supervisee, subservient, respectful relationship, or what is the relationship? What's the mood of both parties? We learn things about the situation, the state, and ideas and location, what's happened before. We can all get this information from speech. So I think it's an important area to work in. And you can get the information, the training data when we're doing AI, but the information for acting on this in a number of different locations. And I think I will just draw your attention really to the mobile devices that we all carry around are able to pick up sound very, very well. And the fact that we can use many different methods of obtaining information, either overtly or covertly. Overtly means that you're aware of it. Covertly means you're not aware of it. So if I was to talk about some random topic, let's say orchids in Singapore, or pirate ships off the coast of Africa, some random thing like that, and then you go back home and you're on your computer and you find out Google's got ads for pirate ships in Africa, or ads to sell you orchids, and you'll be thinking, was it listening to me? Well, I can't answer that. I'm sorry, you've got to make up your own mind, but probably, yeah, why not? This is it's a bit of a page where I kind of say some interesting things that I came across. Some of you might be aware of this one, right? You know this, yeah, I know you know this, yeah. I picked up this research because I was the editor of the journal where he published it. And this is Sri, who published this a few years ago. I said, this is amazing stuff. And I publicized it, I put it in the media. And then the TV went and interviewed him and everything. And they've done this research where they've got a whole bunch of couples going through couples therapy. It's like marriage therapy. They need to go to see a therapist to decide whether they're going to stay together or not. Okay. And these people would go through a series of meetings with the therapist. And it's very simple. The meetings were recorded. Video and audio was recorded as these people met with the therapists. And at the end of those sessions, the therapists, a panel of therapists was asked to listen to all the recordings and see the video and decide, in your opinion, will these couples stay together or not? That's the question. And Sri and his team trained in AI, and they said, let's do the AI to predict the same thing. Will these couples stay together? And well, I mean, you probably guessed the answer here is that the AI was more accurate than the panel of expert therapists. The AI was better able to determine if these people were going to stay together than the expert therapists were. So you can imagine this as an app. So you meet the boy or girl of your dreams, and then you say, hey, let's just see if we're compatible. You start talking to the app. And then after a while it beeps, says, no way, you're never going to stay together. That's where this technology is going. But there's a twist here. Well, I haven't told you. The therapists looked at the video and listened to the speech. The AI didn't use the video. It didn't use the speech contents. It just listened to how people were speaking, the tone of voice, the patterns of speech, the volume. That's all you need to know. How you speak to someone, presumably, is a lot more important than what you say, at least in this kind of relationship. This is just a simple example. Well, it's not simple, but it's just a single isolated example of the kinds of capabilities that we can obtain from speech analysis. I'll just pick out a couple more. There was a German team that I have no idea why they did this. I really don't know what the application is, but they created an AI that detects what you're eating when you're speaking while eating. Okay, now, my mum told me you shouldn't speak while you're eating, but apparently lots of people do this. And they can detect if you're eating jelly or biscuits or peanuts at the same time as when you're speaking. Okay, well, strange. This one, AI number 4, AI to detect lying or evasion in speech. Is where you say to your boss, yes, boss, I think you're great. And actually the thing lights up and it says, nope, that's a lie. Yeah, we can do this to some extent. It's not particularly accurate. I've got a slide on this later. We've all been to the doctor and the doctor's told us what's wrong with us, and then we've got to go home and Google it to find out what it actually means. Well, somebody's done an AI that transcribes the medical speak that doctors speak into what human beings speak. What's actually wrong with you? This is a useful thing. And there's lots of different models, machine learning models that have been developed that can listen to your speech, and they can pick up things like your emotion and your degree of confusion. Very good for students. You can do this visually as well. You look at students, they look, you do need to repeat this again. Lecturers do this all the time. Gender, mental or physical illness, mental illness in particular. I know there's people here working on mental illness detection from speech, and this can be picked up through the way people speak and also what they speak, even whether they speak. One project I proposed to the, I think it was the one of the UK funding agencies, I can't remember which, was a project on alcoholic intoxication. And I prepared an amazing grant. And I said that we can do this for long distance drivers. Instead of having a breathalyzer in the cab, we just have the dispatcher radio them or call them and just talk to the driver for a little bit. Hey, driver, you okay? And just from the speech, they could pick up if the driver was intoxicated. Theoretically, it can be done. My grant proposal was rejected, probably because I put, I think it was like £5,000 for alcohol in the grant. I have no idea why they rejected this, but I was going to send people into the pubs with a recorder and get people intoxicated and then just record their speech. What's wrong with that? Ethically fine, right? Okay. I still want to do it. So if anyone's interested in volunteering on that. Okay, how do we do this? How do we do all this? What's the baseline? Well, I'm going to go through like an arc of technology of how it kind of developed very quickly. And then I'm going to show you where the baseline is of today with machine learning. So keyword detection is where it all started. It's like you have in the films where there's a recording all over the world and somebody uses the word bomb. And then the computer zooms in and finds out someone's on the phone talking about a bomb. And that's keyword detection. It's relatively easy to do if you're speaking a known language. Speech recognition has been around for years, and the ability of speech recognition, it depends on a number of things, including the noise, the number of speakers, the vocabulary, and what's the other thing? The amount of resource you want to throw at it. Sorry, I'll move on a little bit quicker. Many people have seen this plot, which comes from the NIST in the US. It only goes up to 2010, or a more recent one from The Economist that shows on the y-axis, this is what word error rate, I think, on the y-axis, and on the x-axis, it's the year of systems that have been developed. And the different colors show the different tasks for speech recognition, automatic speech recognition. And it shows pretty much year on year reduction in word error rate in a logarithmic scale. Year on year reduction in word error rate for the different tasks. So as we go through time, the word error rate, the error rate of these tasks is getting better and better and better. And the different tasks vary in their real worldedness. Like, for example, meeting speech is quite difficult because it's unconstrained. You can talk about anything. But let's say switchboard is a corpus that has more constrained information in it. There's more constrained pattern. At least it was in the beginning. And on the previous slide, there's some tasks with a smaller vocabulary that are a little bit easier. The great step down from high word error rates to low word error rates came through machine learning approaches. But what we can see, apart from the one on the far right, is they tend to saturate. We throw more and more computing resource at the problem, and it really kind of saturates. And the only question we have is whether the saturation point is better or worse than a human. And the human error is shown on the gray bar on the right over there. Humans get about 4% of words wrong. That's the word error rate. I mean, it depends. In a perfectly quiet place with somebody you know, it'll be less. In a noisy place with people you never met before, you can't see their face, it would be maybe 10% or more. But typically 4% is accepted word error rate for humans. And this is showing that the speech recognition systems that we have, which incidentally I don't work on. I don't work on these directly. They are approaching the level where they are at human degrees of capability. So they're becoming practical. And I would say that they're very useful for transcription, but humans are always best in a tricky situation for now. AI is good for assisting, but not yet entirely replacing humans. Anyone use otter.ai? Okay. Otter.ai is a way of automatically transcribing. You can use it over Zoom, you can use it for recordings, transcribing speech to text. This kind of thing is getting really good, but sometimes they will they will get it wrong, especially if you have a strange accent. It doesn't work with Singaporean speech, I can tell you that. I don't speak Singaporean speech very well, thankfully. Speaker, I'm going to skip through a lot of these. Speaker recognition is who is speaking. This is actually used at the moment in many cases. There's a variant which is speaker verification, which is a binary term. Is the person speaking the person you think it is? So you call up your bank, you say, hey Barclays, it's Ian McLaughlin here. Can you transfer £1 million? Right. I mean, apart from the fact they'll be rolling on the floor laughing at this, they would be needing to verify it's really me that's saying that. They'll use speaker verification technology. Reportedly, they already do. Okay. I think in this task, machines are better than humans most of the time. So we already exceeded human capabilities in this. Language identification. So if you have multilingual situations or recordings where you're not sure what the language is, we can detect very accurately. I've done a lot of work on it. It's probably boring for most people. The difficult thing is discriminating between similar languages. So these tasks, they tend to say, like, let's say Mandarin and Urdu, they're pretty different, right? You don't need to be amazingly good to discriminate between them. But if you wanted to discriminate between this Urdu and Hindi, that's quite difficult. Or English with an Indian accent or English with an American accent, that's quite difficult, usually. It's a lot more difficult than completely dissimilar things. When you've got very dissimilar languages, the computer's way better than humans. When you're looking at fine levels of dialect, right now, trained humans are better. You can defeat these systems, all of these systems, there's ways of defeating them. If you deliberately want to not be subject to this kind of thing. But one of the best ways is something that we do in Singapore very normally. And that is, Singapore is a melting pot of different races. There's 4 main races in Singapore. There's Chinese, Indian, Malay, and we call Eurasian, which is kind of a mixture of everybody. And we typically would have conversations where we mix up all the words. So this thing at the bottom is chi makan with my friend. There's 3 languages in that sentence. You'll hear this all the time in Singapore. We have no real computational tools that enable us to do this. The complexity is, yes, we can detect Indian languages, let's say Tamil, against English speakers from, let's say, Surrey, okay, standard English. But then you get somebody who's Indian that lives in Surrey and speaks English with an Indian accent. How does that work? Or somebody from Surrey that goes to South India and speaks Tamil with a Surrey accent. Is that possible? This kind of thing, yeah, it's really very difficult for computers to find how it works. We have no real way of understanding this. Some of the characteristics of our speech is very much in how we form the acoustics of the sound, and other parts is the words or the phonetic content of what we're speaking. And these things are very confused in speech production mechanism. Let me skip through some of these. Topic detection is about what's being talked about. And there's lots of different subtopics. NIST had a competition up until 2004, where they had challenges on story segmentation. So when a story goes from one topic to another topic, topic tracking, so a story, the tracks of the topic going through a story. Now, how do you piece them together? You know, when you have a novel and the first chapter is 10 years ago, the next chapter is the future, the next chapter is now, this kind of thing. Now, actual topic detection, that is clustering of words around a particular topic. If you ever have, like me, I've got some very strange relatives where you don't know what they're talking about. Usually they can just switch topics completely in the middle of a sentence, and you've got to kind of piece it together. It's hard for computers to do this as well, not just me. First story detection was another NIST challenge, and link detection. This, as far as I know, is not a particularly strong research area at the moment. I may be wrong, but I just think that it's so difficult that nobody is really putting heaps of effort into it at the moment. So this is something for the future. Okay, emotion, thoughts, and feelings. Well, voice stress analysis has reportedly been shown to be better than a polygraph. It says here it's no better than a polygraph. It's because it's unproven, so it's not statistically significant. But the authors of some of the papers I've read, they do claim that it's better than a polygraph. Polygraph is the thing on the right, you know, you get wired up. Yeah, if you've never been arrested by the FBI, you probably don't know what this is. Yeah, you've probably seen it in the films. The really interesting thing, the thing that I found fascinating about this is that all of these tools only work if you have the remotest conscience about lying. So if you can blatantly lie, I've had colleagues like this, you can blatantly lie. They're great to work with, by the way, but if they blatantly lie without blinking an eyelid, without getting concerned at all, then none of these tools will ever pick up that they're lying because they don't get stressed about it. So there's a huge research area. How can we do this? This is a subject of a grant. I just got an email this morning. It's $20 million, and it's on combating the weaponization of the internet. I have a $9.8 million stream in there on how do you tell fake material? How do you tell if somebody is deliberately lying? Right? I'll show you the answer. Emotion recognition. I know people here working on emotion recognition, so probably done a lot more on this than I have. I don't think that our tools are very good at emotion recognition. They're very linguistically dependent, and they're very subjective. And well, at least everything I've ever done, the performance has been quite disappointing. It's an active area of research. We get good performance by reducing the number of emotions. So if you're trying to detect 23 emotions, you might get like 5% performance. So we just say, okay, let's just detect whether happy or sad. Then maybe we can get 90%. That's not really real world, is it? Diarization I mentioned before. Okay, so I'll just skip on a little bit. What we've been looking at is classification of speech. These are all classification things. Is somebody happy or sad? Are they male or female? Are they lying or telling the truth? Or it could be, maybe there's some degree, but they're pretty much classifying things based on labeled information. And they tend to work on a framework that's actually identical. And it looks like this. So at the top, we have training data, and we have a model which we train to make a certain decision. So we do that by extracting features, and we typically use a bit of context around those features, and then we stack them up in some way, and then we just classify those. The type of features that we use, well, everybody in speech uses MFCCs, frequency capsule coefficients. I argue these are not good features. They're designed to mimic the hearing acuity of jazz musicians in the 1930s. So why should you use this for detecting lying or analyzing dog barks, which I've seen? There's other different kinds of features. Oh, people use MFCCs because they're convenient and they work very well. They're not bad. Decision at the bottom here is what you're classifying. It's usually a one-hot label, and you can have the same training material as long as you can label it. This is an ah, this is an ah, this is a l, and you're doing speech recognition. If you say, this is me speaking, this is my wife speaking, this is me speaking, then you're doing speaker recognition. Or this recording in English, this recording in Chinese, this recording's in Urdu, then you're doing language. They're all the same. Same material, just have to have different labels. Techniques are exactly the same. Do you get a paper in one of these fields, cutting edge performance, just switch to a different field and get cutting edge performance in the next field, which I'll show you an example of that in a minute. Okay, I'm going to skip this because of time. That was where we started with speech. Where we moved to was what I call second generation AI-based speech classifiers, where we tend to have two models. And quite often these are based on transfer networks, where you may have a large amount of labeled data from one domain, which you can transfer. Okay, this is all in the slide I just skipped, but you transfer the training power from the big, nicely labeled data set to use it as a feature extractor for a different data set, but then different tasks that you don't have a great amount of labeled data for. And then we end up with features which are an amalgamation, maybe of traditional features, but also with the output from the initial model. And we do the same kind of thing. We take the features and we add context by stacking them over time. And we create them into a two-dimensional block of different features, one per audio frame. An audio frame is about 20 milliseconds long. So you end up with a two-dimensional block. Very interestingly, a two-dimensional block means that you're transforming speech, which is a one-dimensional signal, into a two-dimensional signal. You can now use image processing techniques for the AI decision engines. And you can use any kind of, just name the latest advance in neural networks, whatever it is, you pop it in there. Just take out the old one, put the new one in, get a paper. Okay. Very easy. So this is an example I did 2 years ago. And this one, I just did exactly that. I used different backends and different front ends. And I just flipped between different backends and just flipped between different front ends. And then I got the same architecture that could get the state-of-the-art performance in 4 domains. They got the best performance in language ID, dialect ID, speaker recognition, and speaker verification. So, but it's playing with the system, really. It's all the same kind of data. You're just flipping models. Okay, I've skipped a lot here. Heaps of things. I'm also running out of time. I've skipped the fact that ASR has multiple models. I've really only shown you acoustic type of speech technology. I've skipped something called X vectors and I vectors, which is kind of a big block in speech recognition history that I would get shot for missing out if I was actually lecturing this. And I haven't talked about sequence models, because many things that we do in biological systems are sequences. Phonetics is phones or phonemes are sequenced together. Even our emotions may well be sequenced together. Behaviors are sequenced. So unless we have a powerful sequence modeling tool, we can't hope to understand human behavior from this. It's not instantaneous. I also didn't talk about real-time speech. This all comes from speech communication systems. And I just want to draw your attention to the thing at the bottom of the slide, which is some topics in real-time speech, denoising, removal of echo. You don't know this is happening, but if you've got Apple AirPods, especially the latest ones, then they're doing deep denoising. They're using a technique to extract background noise by producing an internal neural network model of what speech and noise should be like. Bandwidth extension, you can actually use AI to augment an audio signal to get more out of it than it existed previously. And psychoacoustic models tend to model what humans are hearing. Again, I should have removed some of these slides earlier. I'm going to draw your attention to just a couple of things. One is machine translation, that you may have heard some demos of where somebody sits in a room and speaks German and the computer changes it to Spanish. And then someone speaks Spanish and the computer changes it back to German. So this is something that I've done, but not for German and Spanish. I've done it for voice loss patients. So patients that have had their larynx removed, they had a laryngectomy, usually because of throat cancer, and they get the larynx removed. Sometimes it's because of a nerve damage, so that the nerve can't make the glottis work. This is the thing here. So they lose a part of the ability to produce speech. So we've done mappings of degraded speech against the original speech that these people have. So how you train these systems is you get them to say something like, "No, the brown cow jumped over the lazy fox," or whatever. And then you record this, and then when they've lost their voice, you get them to say the same thing again, if you can do that. And then you train a model that maps between them. It's great. It works really well. In the lab, it works perfectly. When there's no noise, and when they say exactly the same thing that you have in the training set, you say something different and it falls out. A bit of noise, dog barks, cat meows, the thing completely dies. They do not work in the real world. Sorry, but they will eventually. I spend so much time on these things. I really, yeah, I keep getting emails from people who've lost their larynx and they're saying, "Oh, Professor, I've seen your research from 10 years ago. You've spent so much money and so much time on doing it. Can you have a system that will help me to speak?" And I've got to tell them that it can't work in the real world yet. It's just not quite ready. I want to talk to you very quickly about audio analysis. I said this at the beginning. There's so many topics in audio that there's just as many topics as there are in speech. And the way I say it is, when we have a computer or a sensor, that if it doesn't understand the sounds around it, it is hearing impaired. If you have a robot that cannot understand sounds, how can you expect it to relate to a human being that can understand sounds? It's just like when you're talking to someone who is hearing impaired. That's not always easy. So if you're working with robots and your robots can't hear, give them hearing. Just let them react to what humans react to. There's three basic technologies that I like to talk about. Audio event detection. That something goes bang in the night and the robot or the computer decides, what was that? The glass shatters. A car backfires. An old lady falls down. They all have sounds, and they have sound signatures which can be learned. Acoustic scene analysis is where your phone, you take it into the lecture theatre and it rings really loudly because you turn the volume up because you were on the street a few minutes before. Okay? Acoustic scene analysis allows your phone to understand the scene that you're in. You're in a meeting, you shouldn't be disturbed. And basic audio understanding. Some examples, really simple examples. If a city council wants to know how well traffic's moving on the street, they can put video cameras, but then a pigeon comes and sits on the video camera, or it snows, or it gets rainy, and the video camera doesn't work. Or it's pointing over there, everything's great over there, but there's a traffic jam over here. Sound travels around corners. Sound is a low-cost sensor. It's low bandwidth. It's cheap. When it gets vandalized, it costs a couple of pounds to replace it. And you can analyze it to find out how fast traffic is moving, how much traffic there is, whether there's pedestrians, what are the pedestrians thinking. You can even use it to analyze how happy people in the city are from the sounds of their voice. We worked on this, we are inspired by nature. So we have three different elements. The external element with the pinner, which is the thing that picks up the sound. Then there's an auditory filtering that happens inside the ear. And then there's the nerves that go into the audio cortex, which is the high level understanding. And my students have almost always worked on something called the Real World Computing Partnership, which is a 50 class audio data set. 50 different types of sounds. And which is considered quite a lot because most academic papers work on smaller sets, although some are very big now. And we corrupt them with noise. So anything that works in the real world, if you don't have it working with noise, it's actually essentially useless as a real system. So we always test with clean and 20 decibels, 10 decibels, and 0 decibels signal to noise ratio. 0 decibel signal to noise ratio is there's as much noise as there is sound. So the thing you want and the thing you don't want are equal levels of volume. That's basically really noisy. And the thing that I told you a few minutes ago about how you stack features to make a two-dimensional map, this was something that my researchers and I, we noticed it back in 2014. And we realized we could start to use image processing techniques. So we published the first deep neural network-based system for recognizing sounds. And then, just like everybody else, CNNs came along, and we thought, hey, why don't we take out the DNN block and put a CNN in there, hit play, train it, test it, and then publish that as well. So we did that the next year, and it was the first CNN-based sound recognition system. And the kind of accuracies we can get, 50 different types of sounds, with very clean speech, we can get about 99% accuracy. And for 20 decibels signal to noise ratio, it's 97%, 10 decibels. So this is noisier than here, much noisier than here. I mean, here is probably like 20, I guess. Sure. You go out on the street, it's probably about, noisy street is 10 decibels. We can get 96% accuracy. Just to say, if you train a system with if you train a system and you don't put noise, so the best system that we had, state of the art at this time, in this level of noise was 13% accuracy, 1-3. Okay, that's lab-based best winning system. RWCP, that data set is great, it's wonderful, but it's not really truly real world, because we get little files and each file has got one sound. It's so convenient. It doesn't happen in the real world. In the real world, sounds are occluded, they're all mixed up. And sometimes you get shh, bang, shh. You've got two things here. Half of that recording is shh, and a little bit is bang. Where is the bang? So we have to identify where a sound is and what it is. And that's continuous audio event detection. It's way more difficult. And we began that in 2017. And this is ongoing with something called the DCASE challenge. This is run by the University of Surrey. I'm going to just, I think for the interest of time, I'll just tell you one more thing here, which is, I told you up front, I don't like MFCCs as features, but everyone else does. So I kind of, okay, I don't worry too much about that. But when we look at a data set and we look at noise, physically, there's different processes happening to create the data and the noise, and they have different spectral characteristics. So what this plot is frequency on the y-axis, so low frequency to high frequency, and it's plotting the cumulative, or that's the average power of the sounds in different frequency bands. So that the purple ellipse, it shows that the orange signal, which is the sound plus background noise, it's got a lot of noise at low frequencies, a lot of power at low frequencies, but the sounds actually have most of their power, in this case, at 4 kilohertz or about 7.5 kilohertz. Okay. And this is very typical of the data sets that we have, that when we look at them, the underlying data and the corrupting noise, or the thing that we don't want, they have different spectral characteristics. So it's a very simple thing. Why don't we create features that maximize the area of the signal that is not corrupted by noise? Right? And we do this with a really simple algorithm where we just forget the stuff on the left, just look at the stuff on the right. Traditionally, people will take a spectrum and they will pull the information from different parts of the spectrum into different frequency bands. And they do either equal frequency bands, or they would do some kind of what do we call it? Critical bands, ear critical bands. But what we've done here is that we have made the bands reflect the difference between noise and signal. I wish I could talk more. I can't talk more about this. I think I just have to skip it through. But what I will say is that we use this and we can get very good results for pretty much any task. It's guaranteed to be better than MFCCs at any task you will want to use. Okay, so machine hearing has got lots of applications. It's exciting, it's great, and you don't want your application to be hearing impaired, so give it some idea of what the sounds are. Machine vision is obviously more popular, and it's much nicer to show at conferences because you've got pretty pictures. You don't have pretty pictures. And NLP is up and coming. So last two slides here. 4 dimensions of future impact, I think, that this kind of field is going to have. First of all, is we are all carrying the computational means necessary and the sensor means necessary. Second thing is you've got 5G coming up and 6G. You can have 1 millisecond latency from your device to a server. There is no need to be limited by the battery power or the computational complexity of your device. You can transfer information at real time. Humans have about 20 millisecond latency. So this is 20 times faster than a human can do anything. Machine learning is always improving, and yeah, what we need to do is get semantic understanding, because we're going here. Short-term applications is things like Alexa Home, understanding the sound environment in your house, not just your voice, but Alexa will say to you, hey, did I hear something go pop in the kitchen? Or Alexa will call you up and say, hey, I think I had somebody fall down in your grandmother's house. Do you want me to call and check? Yeah. And of course, the future is just another rather very intelligent system, Jarvis. It's Iron Man's assistant. When we have something that you can say, hey, can you book me a table at my favorite restaurant at 6 p.m. tonight or whatever? And it does it for you. That's the future. So sorry, that was very quick, but I'm open for questions.
There's some time for questions. Anybody? If not, I'm going to open.
No, please ask.
Thanks very much for your talk. Very interesting. So you mentioned a lot about the opportunities of these systems, but I was wondering, do you ever think about the ethical challenges of the system, and what would be the biggest ethical considerations for them?
Yeah, so the question is a very good one, which is about the ethical considerations and whether I've thought of it. So I worked in China, and the first version of this talk that I ever gave, I gave to the Public Security Bureau. So they wanted me to talk about what they could use speech and audio for public security. And I went and I talked to them, and I told them not all of this, because I hadn't done most of this then, but I told them all this stuff that was really interesting. And then afterwards I thought, goodness, should I have told them this? Yeah. Because then I started hearing stories about them bugging people, but apparently they'd already done most of it anyway, so my conscience is a little bit clearer. And that's when I started to think, okay, we have an ethical obligation to look at the uses of our technology. For us as experimenters, we really need to make sure that we are ensuring that our data is ethically sourced. So, for example, with speech, we need to have the permissions of the people who are speaking, or we need to depersonalize the speech. And in terms of the technology that we're developing, I think we always need to have an idea what the end use is for. If it has an end use which is very benign, like helping kids speak, that's okay. But if it's about being the future thought police, then yeah, I'm not sure if I want to do that. Yeah. It doesn't answer your question because I can't answer your question, but I have thought about it.
We have a more sort of technical question about the last when you showed about the frequency spectrum and this known.
Yeah, did I just skip through it? Sorry, I was really quick. I spoke.
You were showing that in this case, most of the information that you're interested in is in the high frequency bands and the low frequency bands actually not used.
Yes.
It's usually the opposite, right?
Yeah.
Most of the time you're interested in the lower frequency.
Yeah.
So if this method is applied, is it possible to generalize it over different databases, or are you just looking at a particular database with this kind of characteristic?
Okay, you can use it for anything. So let me just tell you this very simply. You've got a neural network, and it's a deep neural network. Let's say a multi-layer perceptor. Okay, and you've got 10 input nodes. Okay, what my technique does is it makes sure that for every single input node, the information that node is receiving has the maximum possible difference between in-class variance and out-of-class variance. It's guaranteed. So I think, although I can't prove it mathematically, you're welcome to try, that this maximizes the ability of the neural network to discriminate between the different classes.
So it does not matter actually where the bit is,
it doesn't matter whether it's it doesn't matter whether it's high or low. So the only thing you have to be a little bit careful of is whether you want to ensure that your data is contiguous or not. So I said that when we take one-dimensional data and we create it into features and we stack it, it becomes two-dimensional and we can use image processing techniques. It's not entirely true because images have correlation in the 2 dimensions. So 1 pixel is correlated to the neighboring pixels on either side and above and below. But if we're now looking at features stacked over time, obviously we always have a correlation in time, but we don't necessarily have a correlation from one feature to the next. So it's not entirely right, but it does seem to work. I hope it answers your question.
Yes, thank you.
Yeah. Sorry, is anybody online has a question? I kind of neglected people online.
People, yes. There would be something on the chat. Mohammed, is there anything on the chat? Yeah. Okay, it's on the chat. So you can post one last question if I can. In one moment, right? You cover all of the different aspects from the very basic signal processing, how to extract information from sound, out of this architecture that accomplish different tasks. But even there are a lot of young people, and some of them might be interested to go in that direction. Where do you see the most promising future, let's say, the most promising things coming out in, let's say, the next 10 years?
Wow. I think that's 2 questions really. So the question is, where's the most promising future? Because there's maybe some young people who think they might want to go into some part of this and investigate it. So I would say that if you're very good at mathematics, then natural language processing is the area to be. Okay, but you have to be good at the kind of mathematics that natural language processing people use. Because it can get very theoretical and quite far away from the underlying language. So I will stay close to the language. I listen to my material. I can hear people speaking Swahili or Arabic or something. Natural language processing people, they're all just tokens. And they process the tokens. And then if you're very mathematical, just look at the things that are coming out with things like ChatGPT and whatever Google's one is called. Bard, yeah, okay, Chatbard. Just look at the things that are happening there. It's very exciting. I mean, do we think that they're going to achieve sentience? I don't know, but do we think that we're going to get to the stage where we can't tell? Yeah, probably. So that's a great area to get into. But if you don't like that kind of mathematics, then I would say there's a lot of areas to get into related to speech and sound. Speech, you have to avoid the things that Google, Facebook, Microsoft, Tencent, Huawei go into. So anything big, anything mainstream, avoid it. Go for the quirky little things. Go for the stuff that they don't do. Go for old people's speech, kids' speech, disabled people. Work with disabled people's speech. That's a great thing to do. Amazing impact. Hearing, again, work with the hearing impaired, work with industrial processes that may not be mass market, work with a company, a print shop, a brewery where there's lots of noise in the background, and look at things to mitigate against that. So the real world aspects are the most interesting. That's my personal view.
Thank you very much. Then I don't know if there is any other question online or in presence. Otherwise, thank you.
Thank you very much. Thank you for your patience and thank you for listening to me talk about what I love talking about.
Thank you.